All right, so let's do an example now of the simplex method. Last time we laid it out and we applied it to the train car example, and let's do another example just to see how this all comes together. So in this case, we have a factory, takes in raw material in the amount of 77 tons. This is TONNES. A TONNE is a metric ton or 1,000 kilograms. It's not the same as a ton, a TON. So that every week it gets 77 tons of raw material, and the plant has the ability to make two different products. So maybe these are two different types of ventilators to help with coronavirus patients. So two different products that use the raw material, and then each product requires different amounts of time and different numbers that can be stored on site and so on. So here's the summary of that. So product A and product B. Product A requires 7 tons of raw material. It takes 10 hours per ton to produce, and the plant can only store up to 9 tons per week. And the profit is 150 per ton. Again, like in our last a couple examples ago, it could be $150, $150 million, whatever unit you want to put on there. Similarly, product B requires 11 tons. It takes 8 hours per ton to produce, and the plant can only store up to 6 tons per week, and the profit is 175 per ton. Now, the plant can be run for 80 hours per week, and so we have clearly a bunch of constraints, and the idea will be to determine how much product can be made, product A and product B, such that we maximize the profit. So that's our objective. So let's formulate the problem. So we have two design variables, x1 and x2, will be the tons of product A produced each week and the tons of product B produced each week, respectively. So x1 and x2 are how much of A and how much of B are made each week. So the objective function, I'm going to call it J bar. And the reason for that is because we're maximizing profit. So we're going to pose it first as a maximization problem and then convert it to a minimization problem in terms of J. So I'm going to call this J bar. And that's 150 times x1 plus 175 times x2. However many of product A we make, multiply that by 150. However many of product B we make, we multiply that by 175. And we want to maximize the profit, so maximize J bar. Now let's walk through the constraints. The total raw material that we bring in each week is 77 tons. And product A requires 7 tons, product B requires 11 tons. So 7 times x1 plus 11 times x2 has to be less than 77, less than or equal to 77 each week. We obviously can't use more raw material than what's available to us. The total time of production can't exceed 80 hours per week. So that's 10 hours to make product 1 plus 8 hours to make product 2 has to be less than 80, the total number of hours per week. In terms of storage, we can't store more than 9 of product A or 6 of product B. So x1 is less than or equal to 9, x2 is less than or equal to 6. And then finally, we have our positivity constraints. X1 and X2 obviously have to be greater than 0. We can't make a negative number of products. All right, so now we want to put it in standard forms. Remember what the standard form looks like, and then we'll walk through the steps to get it into standard form. So the first thing is the objective function needs to be such that we are minimizing the objective function. So instead of maximizing J bar, we'll minimize J, which is the negative of J bar. So then J, our objective function, is minus 150 x1 minus 175 x2. So we're going to minimize that, which is the same as maximizing the total profit. Then we have several inequality constraints. We just laid them out, and we'll introduce slack variables to convert them each to equality constraints. Let's actually go back here and think about N, M, and S. So remember, N is the number of design variables, of which there are 2, so n is 2. M is the number of equality constraints, of which there are none. So M is 0, and then S is the number of inequality constraints, of which there are 1, 2, 3, 4. So N is 2, M is 0, and S is 4. All right, so now let's come back to this. So now we have our 4 inequality constraints, which we convert to 4 equality constraints. And you'll see, remember 7x1 plus 11x2 has to be less than or equal to 77. So we just introduce a slack variable s1 so that we can make this an equal sign. Likewise, 10x1 plus 8x2 has to be less than or equal to 80. So we add in a slack variable s2 to make that an equal sign. x1 has to be less than 9. We add in a slack variable s3 to make that an equality constraint. x2 less than or equal to 6. Remember, these last two are the amount that can be stored. x2 has to be less than or equal to 6, so we add a slack variable s4 to accommodate that. So we have 4 slack variables, 1 for each of our inequality constraints. So here's what I said before. So n is 2, m is 0, and s is 4. So what does that mean for the non-basic and basic sets? So remember, n minus m, which in this case is 2, that's the number of non-basic variables. That's the number of variables that must be 0 at the optimal solution. The remaining variables, of which there are 4, must be non-zero. So where do we get the 6 variables? We have 1, 2, 3, 4, 5, 6. N, which is 2, plus 1, 2, 3, 4, S to make 6. So 6 total variables, 2 are 0, and 4 are non-zero at each basic feasible point, which are the vertices of our polygon. Okay, so let's draw this feasible space so we can see what this looks like. So this is going to be x2 versus x1. And the positivity constraints say that x1 has to be positive. So this is the x1 equals 0, the left boundary. And they say that x2 also has to be greater than 0. So again, we're in the first quadrant as always once we impose the positivity constraints. So x1 and x2 equal to 0 correspond to the vertical and the horizontal axes respectively. All right, let's go back. So that takes care of the positivity constraints. Let's look at these two first. So let's look at these two first. So x1 plus s3 is less than 9. Let's take a look at that. So let's put some tick marks on here. So if this is 10, say, then this will be 9. So we have that x1 can't be more than 9. So to the left of this, which corresponds to S3 is equal to 0, the feasible space has to be to the left of that. Similarly, the last one, x2 plus s4 has to be equal to 6. So if I make this, let's make this 5, and then 10, and then we're going to need 11, but less than 6. So right here, say. So we have, this has got a little too close, let me do that. So this corresponds to S4 is equal to 0, so it has to be less than that. So x2 is less than 6. If x2 is equal to 6, then we're on this line and there is no slack, so S4 would be 0. If we're somewhere less than 6, then S4 is positive. All right, now that takes care of these two right here. Now let's look at the other two. Which one to do first? Let's do this one. So let's just work backwards, continue working backwards. So let's do this one right here. So 10x1 plus 8x2 plus s2 is equal to 80. So let's just assume that s2 is equal to 0, and we'll draw that straight line in the x1, x2 space. So you get the y-intercept and all of that. The y-intercept is 10 for this one, and it's going to go down to 8, I believe. Is that correct? Yes, 8. So this will be 8. So it goes from 10 to 8. So this corresponds to, what did we say? S2 is equal to 0. And so it has to be less than that. So it has to be below it and to the left. I know these can get a little confusing. All right, then we look at the first one, 7x1 plus 11x2 is equal to 77. So that's the boundary, which would correspond to when S1 is equal to 0. So that puts us 5, 6, 7, and it goes to 11. So it goes from here to here. So this corresponds to S1 equals 0, and it's, again, below and to the left of that. All right, did I get that right? Did I get that right? Let's just double check. And I think I did. Thank you, thank you. All right. Okay, so a couple comments about this. One thing you'll notice, and this happens sometimes, is the S3 equals 0 constraint, that's this one right here, is actually redundant. Because if you look at where the feasible space is, let's draw this in, say, red, it's where all of these are satisfied, which corresponds to, let me just put hash marks in here, corresponds to this region right here. So that's the region where all of the constraints are satisfied. And what you'll notice is for this one, for the S3 is equal to 0, it doesn't impact on that space at all. So we say it's redundant. It doesn't actually add anything in terms of limiting the in terms of limiting the feasible space. So we have how many basic feasible solutions? Remember, the basic feasible solutions are the corner points of the resulting polygon. So let's, and I messed up my, what a bummer. See if I can try to erase this without doing too much damage. Sorry about that. Yeah, I know, that was unfortunate. All right, so this is my feasible space. Sorry, I got that extra little triangle that didn't belong. Okay, so now let's label these points in blue. So let's start down here. This will be A, then B, C, D, and E. So those are the corners of the polygon that define the feasible solution. Okay. Now, our job is to figure out whether A, B, C, D, or E is the corner point, the basic feasible solution, which minimizes our J. our objective function. That is the objective. All right, so let's just make a table to kind of keep our head on straight. So we have the 5 points A, B, C, D, and E, and each one of those corresponds to 2 of the variables being 0. So you can see which 2 they are. So at point A, it's where x2 is 0 and where x1 is 0. That's the intersection of those 2 lines. Point B is where x2 is 0 and s2 is 0. x2 and s2. And you can go through C, for example, is where these 2 cross. That's the s2 and s1 is equal to 0 line. So s1 and s2. Then finally for D and E, s1 and 4, and x1 and s4. So you can get, in this case, we can get that straight from the feasible space plot. If you can't plot it, obviously, you'll have to go back and look at it in a little bit more depth. All right, so these are the 5 basic feasible points. One of these is the optimal point. That's the one we're looking for. And we know, corresponding to each point, which of the 2 variables are in the non-basic set, the ones that are 0. So we can form our Simplex Tableau. Here it is. It's a little more complicated this time because we have 1, 2, 3, 4, 5 equations. Remember, 1 objective function plus 4 equality constraints that were originally inequality constraints. We have 1, 2, 3, 4, 5, 6 variables in the x vector and a 7th value variable, which is our objective function. So 1, 2, 3, 4, 5, 6, 7. So this is 1, 2, 3, 4, 5 by 7, which again corresponds to the fact that 2 of these variables have to be, well, not j, but 2 of these variables have to be 0. Does that make sense? It wasn't a very good, it was supposed to be like, I get it. Anyway, moving right along. So that's our Simplex Tableau. We could do like we did in the previous example and take out the 2 for each of our 5 points, the 2 variables that are 0, and then solve the system. But let's walk through this in a method that would be more akin to what you would do in the Simplex algorithm itself. So the Simplex algorithm, remember, the first step is to decide where to start. Again, I'm not going to get into the details of how the Simplex algorithm does that. We're just going to simply start with point A. Point A would be we're not making anything. So x1 is 0 and x2 is 0. Obviously, we can do better than that. So this A is not going to be the optimal point, but we'll start there just to get things rolling. And so for point A, which is when x1 and x2 are 0, if you go back and look at J, which makes perfect sense, if you're not making any product, then you're not making any profit. So J is equal to 0. Now remember, it's a minimization of J. So the more negative the value is, the better. And then when you take the negative of that gives you a positive number. That's the profit that we're trying to maximize. So starting from point A right here, we would just decide, do we want to go and do B next, or do we want to go and do E next? And again, the Simplex algorithm has intelligent ways to figure that out. We're just going to go straight to B and see what happens. So in the previous table, B being 0 corresponds to when x2 and s2 are 0. And when you put in x2 and s2 are 0 and you solve for j, you get minus 1,200. So that's a candidate. It is certainly more negative than 0. So that would be a candidate for the optimal solution. Then you proceed to C. When you're at C, S1 and S2 are equal to 0. And so then you calculate when S1 and S2 are equal to 0, what's J? And that's minus 1,413 and 89 cents, or again, whatever the units are of this number. And it turns out that's the smallest value. If you were to continue on to D, then this value would increase. J would go up, and we would find that this is the minimum J. That's the J, the maximum profit. The negative of that is the maximum profit we can make. and it corresponds to point C when S1 and S2 are equal to 0. Okay, so again, the simplex algorithm would determine the order in which we evaluate the basic feasible points as we proceed around our polygon from vertex to vertex. And basically what it does is it looks for the direction that has the greatest decrease in the objective function. So starting with point A, which one, B or E, would give me the greatest decrease in the objective function, and we hope that that's going in the direction that will give us the minimum. So that again leads us from A to B to C. And then point C corresponds to the maximum profit per week, which is 1,413 and 89. All right, let's finish up with some comments. So I've already mentioned that Tableau is just a fancy French word for table. Simplex is a little less common word. It's obviously not something we normally use in our everyday English language. Simplex is the simplest polygon or polyhedron in each dimension. So, for example, in one dimension, the simplest polygon would be a line segment. In 2D, it would be a triangle. In 3D, it would be a tetrahedron, and so forth. So geometrically, that's what we call the simplex. We're denoted by that term. Linear programming codes are very complex. The basic ideas are quite simple and straightforward, as we've gone over in this chapter, but to actually write a code that does this and makes all these decisions, again, emphasizing the where we start question and in which direction do we go question, these can get very, very complex, and they have to be able to handle all kinds of eventualities, of which we'll discuss in a second, some of the various things that can happen. So again, how to choose the starting basic feasible solution, and then how to choose in which direction to proceed. So we have what are called leaving and entering variables. So every time you go from one vertex to the next, you're going to have one of the two variables in this previous example. We have one of the two variables leaving the non-basic set and one of them entering the non-basic set. So again, the algorithm has to determine how best to do that. There is a slightly more advanced technique. It's called the interior point method, and it can take advantage of the fact that in some cases, especially when you have very, very large numbers of design variables, so you have a very, very large polygon with many basic feasible solutions, it allows the algorithm to actually go across the feasible space rather than being limited to going from one vertex to an adjacent vertex to an adjacent vertex. So in principle, obviously, it makes sense that that could be faster. The devil's in the details in terms of how you program that and how you make that decision to scoot across the entire feasible space to another vertex. But again, there is another alternative to the simplex method that can sometimes be faster. You'll notice my qualifying adjectives there, sometimes, maybe, possibly, because it's not so straightforward how you would actually implement such a thing. And then finally, there are various possibilities, and I've kind of hinted at these, but let's be more explicit. So there's 1, 2, 3, 4 possible outcomes of an optimization problem. The first one is the desired one, and that is where you get a single unique optimal solution where it minimizes J and it occurs at one of the vertices, one of the corners of the feasible space. So that's generally the most desirable solution because there's only one optimal solution in that case. You could have an infinity of optimal solutions. So that literally means there's an infinity of possible values of the design variables, as well as the slack variables, that give you the smallest value of J. That would occur, it's not hard to imagine, that would occur if the lines of constant J are parallel to one of the boundaries of the feasible space. So again, just picture the feasible space, it's a polygon, and there's no reason why it couldn't be the case that if you were to draw lines of constant J, we talked about this a couple of videos ago, that they would actually be parallel to one of the edges of the polygon, in which case, rather than just one vertex giving you minimum J, that whole edge would give you minimum J. So the line segment between two adjacent vertices would be the optimal solution, of which there's an infinity of points on that line segment. So there could actually be an infinity of solutions. So this is the most desirable. This one, there's still an optimal solution. In fact, there's an infinity of optimal solutions. The third possibility is if the feasible space is not closed, it's not a closed polygon. So you can easily imagine in this last example that depending on what the inequality constraints are, you could end up with a situation where you don't have a closed polygon in the end. And so in that case, you can think of the J as it spills out of your feasible space, becomes infinite, and therefore J could be at infinity. So that's generally speaking not a desirable outcome. Now, if J was profit and you could have an infinite profit, that would be great, but that probably means that you missed something in your setting up your optimization problem. You forgot that you only have a certain number of employees and they can only be working a finite amount of time or some such thing. So that's an undesirable outcome. Another undesirable outcome is if the constraints are not consistent. So once again, if you look back at that example that we just did in this video, you could easily imagine a situation where the inequality constraints would be such that it basically leaves you with no feasible space. The feasible space is the null space. There's no points in the x1, x2 plane that satisfy all the constraints. So that would obviously be an undesirable outcome. So the last two usually mean that you have not formulated the optimization problem correctly, you've missed something, or if you have formulated correctly, then you need to go to your boss and tell them that this just isn't going to work. There is no optimal solution, or there optimal solutions at infinity, which obviously is not something that can be done in practice. The first one is the most desirable. Second one is an okay outcome, but again, it gives you an infinity of possible optimal solutions. The third and the fourth option are, again, means that you need to do more work. All right, so that completes the optimization chapter. You can now do problem set 6, and that will be due in a week. I'll email about that.